A Formula One car can exceed 300 kilometers per hour, yet its core begins as a black sheet lifted from a freezer. Technicians layer this carbon into a
Clamp the
survival
layers
cell,
down.
like the one that let a driver walk away after an impact tore the engine and gearbox from his car. The car is built twice, first in invisible air, then in carbon, metal, and code. Before it can race, controlled loads and impacts will probe that structure for hidden weakness. Black material is carbon fiber prepreg. Carbon fibers already combined with a carefully controlled resin. It can be cut with a blade, bent by hand, and placed into a mold one layer at a time. Eventually, it will surround the driver and carry loads through the entire car. It will also become one part of a machine containing an extraordinary number of components. Mercedes currently tracks more than 14,500 individual parts in each of its race cars. While one car is still racing, engineers are already designing its replacement. Concept work can begin more than a year before the new machine is due to compete,
another mold and put
especially
into the
when a
larger
major
oven for
regulation change is approaching. Even then, the process does not begin with an engine. It begins with a rulebook. Formula One is called a formula because every car must obey the same technical framework. The regulations define mandatory safety structures, permitted dimensions, reference volumes, material restrictions, minimum mass, and areas where bodywork may or may not exist. The rules do not tell a team exactly what its car should look like. They create a legal space inside which engineers must find their own answer. Think of the regulations as a complicated fence. Every team starts inside the same fence, yet the cars emerge with different floors, cooling systems, suspension layouts, wings, and body shapes. That difference begins in the air. Long before a physical chassis exists, engineers create a digital version inside computer-aided design software. Separate groups work on aerodynamics, composites, suspension, transmission, electronics, structures, and cooling, but no department can work in isolation. A decision made by one group can create problems for several others. Aerodynamicists are not simply drawing a sleek exterior. They are assigning a job to nearly every surface. The front wing must generate useful load, while managing the disturbed air created by the front wheels. The floor must accelerate air beneath the car and create low pressure. The bodywork must guide airflow toward the rear while allowing the machinery inside to breathe. Cooling inlets must admit enough air without producing unnecessary drag. Brake ducts must control temperature while operating in an aerodynamically sensitive region. Even the position of an internal pipe can affect the external bodywork wrapped around it. Change one surface, and the air reaching another surface may change as well. A front wing adjustment might improve the front of the car, but disturb the floor farther downstream. A smaller cooling inlet may reduce drag, then leave the power unit too hot. More downforce may increase grip, but it can also increase structural loads and make the car less efficient on a straight. Engineers begin testing these relationships with computational fluid dynamics, or CFD. Instead of placing a real car in real air, powerful computers divide the virtual space around a digital car into an enormous number of small cells. Equations estimate how pressure, velocity, and turbulence behave through each region. CFD allows engineers to examine things that would be almost impossible to see on a moving car. They can follow vortices, compare pressure maps, and investigate how airflow changes when the car turns, brakes, rides over a bump, or enters the wake of another vehicle. The result is still not a final answer. It is a prediction. Promising ideas move to the wind tunnel, where the digital car becomes physical, but not at full size. Under current FIA operational rules, an F1 wind tunnel model can be no larger than 60% of the real car. Its components must still be manufactured with extraordinary precision because a tiny change in geometry may alter the measurement. The model runs above a moving belt that represents the track rushing beneath the car. High-velocity air passes over it while sensors measure aerodynamic forces and pressures. The model can steer, rise, fall, pitch, and roll. Engineers can reproduce different cornering attitudes, compare ride heights, and study what happens when the car is no longer traveling perfectly straight. The wind tunnel provides physical evidence, but it is still not the racetrack. The model is smaller. The environment is controlled. Real tires deform, wind changes direction, track surfaces contain bumps, and another car can fill the air with turbulence. So the team compares one prediction against another. CFD against the wind tunnel against the simulator, and eventually all three against the real car. This creates the first version of the machine. Before it becomes carbon and metal, an F1 car exists as an interconnected map of airflow, forces, temperatures, and compromises. But the digital car has no seams, no manufacturing defects, and no deadline at the airport. The factory must now make the prediction survive physical reality. That requirement can change the design before a single race component is produced. A shape may perform brilliantly in simulation, but be too fragile, heavy, or difficult to reproduce. Engineers must consider where a mold can separate, how a technician can reach an internal surface, where the fibers should run, and how the cured component will be trimmed and inspected. A design that cannot be manufactured consistently is not a design. It is an expensive illustration. For many carbon composite parts, production begins with tooling. The team first needs a mold whose surface is essentially the negative of the component it wants to create. Depending on the application, this may involve machining a master pattern and using it to produce a composite mold, or manufacturing the tool from another dimensionally stable material. The choice depends on temperature, required accuracy, production quantity, and how much the tooling may expand during curing. Surface quality matters. An unwanted ridge or distortion in the mold can be copied into every component made from it. While the tools are prepared, rolls of prepreg carbon fiber wait in cold storage. The low temperature slows the chemical activity of the resin and extends the material's usable life. Once removed, the prepreg must reach the correct working condition before its packaging is opened. This reduces the risk of moisture forming on the material. From the freezer, it enters a tightly controlled composite area. Temperature, humidity, dust, and handling all matter. Contamination trapped between layers may interfere with a bond or create a defect that disappears from view after curing. The black structure of an F1 car begins in a room where an invisible mistake may have a very visible consequence. Computer-controlled cutting machines slice the prepreg into carefully designed shapes called plies. These pieces are organized into kits, often with identification and tracking information so technicians know exactly where each layer belongs. What looks like black fabric is actually a directional structural material. Carbon fibers are extremely strong along their length. But a single sheet is not equally strong in every direction. Engineers specify the angle of every ply according to the forces the finished component is expected to carry. One layer may run lengthwise. Another may cross it. Others may sit at diagonal angles to resist twisting or loads arriving from several directions. If you bend a single unidirectional sheet across its weakest direction, it can feel surprisingly fragile. Align those fibers with the load, and the same material behaves completely differently. The order matters. The orientation matters. Even the position where one ply overlaps another can matter. Technicians lay the pieces into the mold according to a detailed laminate schedule. Laser projection systems may illuminate the exact boundary and orientation of each ply, but complex surfaces still depend on skilled hands. The material must follow tight curves without folding. It must sit correctly around inserts, corners, and transitions. Air cannot be casually trapped between the layers. The number and direction of those layers can determine more than whether a component survives. Engineers can also tune how and where a carbon structure flexes under load. A part may be extremely stiff in one direction, while allowing a carefully controlled amount of movement in another. This can help manage loads or create useful mechanical behavior without adding a conventional joint. That flexibility is closely regulated. Real wings and bodywork are never infinitely rigid, so the FIA applies load and deflection tests intended to distinguish normal elastic movement from prohibited aerodynamic behavior. Carbon fiber is not simply a light replacement for metal. It can be engineered as both a structure and a spring. Some components use a lightweight core between carbon skins to gain bending stiffness without becoming solid carbon. Metallic inserts can also be positioned where the structure must accept bolts, bearings, or other attachments. The exact combination depends on the part. A wing element, floor section, body panel, and survival cell experience very different loads. Once the layup is complete, the part is prepared for curing. Layers of release material, breather or flow media where required, and a sealed vacuum bag are arranged around the laminate. Vacuum draws air from inside the bag and compresses the material against the mold. Technicians check for leaks. A poor seal could leave air inside the laminate, creating voids that weaken the finished component. The bagged mold enters an autoclave, a large pressure vessel that applies a controlled combination of heat, pressure, and time. This is sometimes described as baking carbon fiber, although baking a cake rarely involves vacuum lines, structural inserts, and a laminate intended to carry a racing car. As the temperature rises, the resin flows and then chemically cures. External pressure helps consolidate the layers, while the vacuum removes trapped gases. The exact cycle depends on the material system, laminate, and component. It also creates an unavoidable manufacturing limit. An autoclave cycle cannot simply be rushed because a replacement floor is needed at the next Grand Prix. The resin does not care about the freight deadline. After cooling, the component is released from its mold, excess material is trimmed away, holes and edges are machined, and bonded assemblies may undergo additional preparation and curing. A flawless surface can still conceal a structural defect. Teams use dimensional inspection and non-destructive testing methods suited to the component. Ultrasound, X-ray, and other techniques can reveal voids, delamination, or poor bonding without destroying the part being examined. The carbon is now rigid. That still does not prove it is safe. The most important composite structure is the survival cell, the shell built around the driver. Carbon fiber became central to this role only after a major historical gamble. Earlier F1 monocoques were commonly assembled from aluminium sheet and internal bulkheads. They could be light and stiff by the standards of their era. But engineers saw the potential for something structurally more efficient. In 1981, McLaren introduced the MP4/1, widely recognized as the first Formula One car built around a complete carbon fiber composite monocoque. Designer John Barnard worked with the American aerospace company Hercules because the necessary experience was far more common in aerospace than in motor racing. The early chassis did not emerge from a mature or familiar process. Some of its major surfaces were flat because manufacturing complex curved carbon structures was still difficult. Many people inside Formula One doubted whether the unfamiliar material could survive a serious impact. Then came the evidence. During the 1981 Italian Grand Prix at Monza, John Watson suffered the crash teased at the beginning. The engine and gearbox were torn away, but the carbon monocoque surrounding him remained intact. Watson walked away. Carbon fiber was no longer merely an exotic way to reduce weight. It had demonstrated a new approach to stiffness and survival. Modern composite construction is vastly more sophisticated, but that central idea remains. The survival cell is not decorative bodywork wrapped around a conventional frame. It is the main structural shell of the car. The driver sits inside it. The flexible fuel cell is housed within it. The front impact structure attaches ahead of it. The power unit attaches behind it, while side impact structures help protect it against lateral forces. Our modern car's external bodywork is also largely composite. But not every black surface performs the same job. Some panels primarily guide airflow or cover internal systems. The survival cell must preserve a protected space around the driver under severe loads. Once that shell is complete, the factory begins adding the car's mechanical organs. Multi-axis CNC machines cut components from billets or forgings of aluminium, titanium, steel, and other permitted materials chosen for specific combinations of strength, stiffness, mass, and temperature resistance. A block of metal may spend hours inside a machine while cutters remove most of it, leaving behind thin walls, internal passages, and precisely controlled mounting surfaces. Some components may also use additive manufacturing when their internal geometry would be difficult to machine conventionally. The printed object is rarely finished when it leaves the machine. It may still require heat treatment, machining, surface finishing, and inspection. Suspension systems bring the material worlds together. Carbon composite members may connect to carefully manufactured metallic fittings, bearings, uprights, and hubs. Every connection must position the wheel accurately while surviving braking, cornering, and curb impacts. The power unit may come from a manufacturer linked to a works team or from an external supplier. Other parts may arrive from approved suppliers or technical partners. And F1 Factory does not necessarily manufacture every object found on the car under one roof. Its real job is to make all those objects behave as though they were designed as one. The power unit mounts behind the survival cell and becomes part of the load-bearing structure. The transmission sits behind it and leads toward the rear suspension. Around that structural chain, engineers must package radiators, electrical systems, energy storage, exhausts, pumps, reservoirs, cooling pipes, and wiring. The air wants the car to be narrow and clean. The machinery inside demands space, cooling, and protection. Every performance gain sends an invoice to another department. Reduce a cooling inlet, and the aerodynamicists may gain efficiency, but the thermal engineers must prove the power unit will remain within safe temperatures. Move a component inward, and the bodywork may become tighter, but mechanics may struggle to reach it between sessions. The team is not manufacturing the best possible collection of individual parts. It is manufacturing the best compromise that still behaves like one machine. Every component can be correct on its own, and the complete car can still fail. Final assembly must now prove that every department designed the same machine. The survival cell becomes the spine of the build. Technicians install the fuel cell, controls, wiring looms, hydraulic lines, cooling connections, and sensors. Our wiring harness may not attract the same attention as a front wing, but it must survive heat, vibration, fluid exposure, and repeated maintenance. One poor connection can stop a car filled with otherwise perfect components. Cooling circuits must be sealed. Hydraulic systems must respond reliably. Sensors must report pressure, temperature, displacement, and acceleration so engineers can understand what the machine is doing. The seat is formed around the individual driver rather than selected from a shelf. Pedal positions, control reach, belts, head protection, and cockpit padding must meet ergonomic and safety requirements inside an extremely restricted space. The power unit and transmission are joined to the chassis. Suspension assemblies, brakes, and steering components follow. The floor and body panels enclose the internal systems, and the wings complete the visible shape. Distinction between appearance and engineering becomes clear when examining a commercial show car. It may wear carbon bodywork, an exact livery, a convincing steering wheel, and even a molded seat, yet use a dummy frame where the engine and gearbox should be. Some lack working brakes, radiators, and race-spec tires. From a few meters away, you might not notice the difference. Visual accuracy is not mechanical authenticity. The real machine continues through a much harsher process. Fasteners are tightened to controlled specifications. Clearances are measured. Assemblies may be installed and removed repeatedly to confirm fit and access. Metrology equipment compares manufactured components with their digital definitions. Coordinate measuring machines, scanners, and specialized gauges can reveal whether a part has warped or been machined outside its permitted tolerance. Every important component also receives an identity. Teams record when it was manufactured, installed, removed, inspected, and returned to service. And here comes the reversal. A part can be perfectly manufactured, pass every inspection, and still have an expiration date. Highly loaded and safety-critical components are assigned controlled service lives based on mileage, operating time, load cycles, and inspection history. Many parts are not installed and forgotten. Some assemblies may run for roughly 2 race weekends, about 1,200 kilometers, before being removed for another round of examination. Depending on the material and failure risk, X-ray, ultrasound, or dye-penetrant inspection may reveal internal damage or surface cracks invisible to the eye. A part returns to the car only after it has been cleared again. The factory is therefore not simply producing new components. It is managing the changing condition of components that already exist. A complete car may now sit on its wheels, wearing a polished livery and looking ready to race. Looking finished does not mean the car has been proven. Individual components may undergo proof loading and fatigue testing. Suspension assemblies can be exercised on rigs. Gearboxes and power units run on dynamometers. Pumps circulate fluids, and cooling systems are pressurized to reveal leaks. Engineers are not looking only for catastrophic failure. They are searching for friction, delays, overheating, unusual vibration, or a measurement that does not agree with the model. The survival cell faces the most dramatic proof of all. FIA regulations prescribe impact and static load tests for the chassis and its safety structures. The precise procedures evolve with the rules, but the purpose remains consistent. Prove that the car absorbs energy where it should, while preserving the protected space around the driver. Front and rear impact structures are designed to deform in a controlled manner. That deformation is part of their job. By absorbing kinetic energy progressively, they reduce the forces transmitted toward the survival cell. The central shell has a different task. It must resist intrusion and maintain its integrity around the cockpit and fuel cell. Static tests apply major loads to prescribed areas while engineers measure deformation. Impact tests drive assemblies into barriers under controlled conditions. Significant structural modifications may require further testing because passing with one design does not automatically validate another. Watson's crash at Monza proved what a carbon survival cell could do in the real world. Modern teams are not allowed to wait for another accident to discover whether their structure works. They must prove it before the car races. Some test pieces will therefore never reach a circuit. They exist to be loaded, struck, or broken so that the components which do race can be trusted. This closes the mystery of the black sheet from the beginning. Carbon fiber does not protect a driver simply because carbon is a remarkable material. Protection comes from fiber direction, laminate sequence, bonding, load paths, manufacturing control, and verification working together. Safety is not added after the fast car has been built. It is manufactured into the structure from the first ply. Passing those tests proves the chassis can legally and structurally exist. It still does not prove that the complete car will be fast. Then comes one of the most emotional moments inside the factory. The first fire-up. It may happen before the car looks complete. Bodywork can still be moving through production, leaving the survival cell, power unit, transmission, cooling system, wiring, and fluid lines exposed. For the first time, thousands of separate drawings must behave as one machine. Electrical systems communicate. Pumps activate. Fluids begin to circulate. Engineers watch pressures, temperatures, and signals across the car. Then the power unit fires. The sound is brief evidence that the manufactured systems can finally breathe together. The bodywork returns. The floor is installed, and the finished car is weighed. Even the livery becomes an engineering decision. Paint and vinyl add mass, which is one reason teams sometimes leave areas of carbon fiber visibly exposed. At last, the car reaches a circuit for a permitted shakedown or official test. For spectators, this looks like its birth. For the engineering team, it is the first complete experiment. Sensors measure the behavior of the physical vehicle. Engineers compare aerodynamic loads, temperatures, suspension movement, tire behavior, and driver feedback against predictions made months earlier. If the measurements agree, the digital model, wind tunnel, and real car are correlating. If they do not, the investigation begins. Perhaps the car is running at a different ride height than expected. Airflow may be separating from a surface. A structure might be flexing in a way the model did not capture, or the tires may be changing the car's platform more than anticipated. The first lap does not finish the manufacturing process. It sends a new set of instructions back to the factory. Designers revise geometry. Composite technicians prepare new molds and layups. Machine shops schedule updated components. Inspectors validate replacements. Production managers decide how many examples can be completed. And logistics staff determine whether they can reach the next circuit. This is another race that viewers rarely see. A new part is not useful merely because simulation predicts a performance gain. The team must manufacture it consistently, inspect it, install it, and produce enough spares. A delicate wing that works once but cannot survive normal circuit use is not a real improvement. Time inside an autoclave cannot be negotiated. Machining capacity is finite. Inspection takes time. The cost cap forces teams to choose which ideas are valuable enough to become physical objects. During the season, the original car branches into different configurations. High downforce circuits may require one wing package, while faster tracks demand another. Cooling openings change with temperature and altitude. Floors, wings, and suspension details evolve as the team gathers evidence. Damage creates another manufacturing cycle. A broken front wing, cracked floor, or expired component must be repaired or replaced while production continues for future upgrades. The factory is not building one car. It is maintaining an evolving population of structures, spares, and specifications, all connected to the same design history. Return to that first sheet of carbon fiber. At the beginning, it looked impossibly far removed from a Formula One car. Now it carries the entire process inside it. Digital airflow, fiber angles, human precision, controlled flexibility, vacuum, heat, pressure, inspection, structural testing, and finally track data. A Formula One car is not one machine built once. It is a chain of predictions made physical, tested under load, and rebuilt through data. When the finished car leaves the garage and accelerates onto the circuit, its manufacturing journey appears complete, back at the factory. The next version has already begun,